All right, hey crew, I'm going to go ahead and do a video for today's lesson because I had forgotten that I needed to take my little man to a doctor's appointment during your class. So I would love to do this class in class just so I can make sure that we really have the understanding. But there's a lot of key parts to this that I want to make sure that we are understanding. So if you have any questions along the way, please make sure that you ask or write them down so that you can ask tomorrow. Also, if there is something that doesn't seem to be making sense, think about going back, stopping the video, going back and rewinding it, and trying to listen to it again to see if that can help you. Because what we're going to be doing now is we're going to start solving our polynomials, and we are going to be using our division in order to do this. So you'll remember the other day when we talked about the fundamental theorem of algebra, which it tells us exactly how many solutions we are going to have to our polynomial. And that being said, if we have a quadratic, like I see here, I see the degree of my polynomial is 2, so there has to be 2 solutions. Now, it is possible for those both to be real solutions. It is possible to have only one real solution with a multiplicity of 2, and there's also a possibility of us having 2 imaginary solutions. We're going to be working with just real zeros today. So x squared plus 3x minus 28. Now, this is one that if we had defined the real zeros, we could do that because we can factor this out. X squared, that's x times x, and negative 28. I want to find 2 numbers that multiply to be negative 28, but at the same time add together to be 3. So if I do a positive 7 and a negative 4, that should do it for us. Since we are finding the real zeros, since we want to find the real zeros, we are looking for where does this graph cross your x-axis. So when is it that y is equal to 0? So now I can use my zero product property. If x plus 7 is equal to 0, we can say that x minus 4 is also equal to 0. Subtracting 7 from both sides, x can equal negative 7, and x is equal to positive 4. And back to our chapter last time, if I was to graph this out, I have a solution at negative 7. I have a solution here at positive 4. And there's my parabola that we're looking for. Now, what also can be said with this is that the big part of this here is that we are coming up with the factors. So a factor is x plus 7 and also x minus 4. Because those are factors, and one thing that we were talking about yesterday with the, I'm trying to think off the top of my head, the factor theorem, is if we have factors, then what that means is that they can divide into our polynomial evenly. So for example, if I was to take f of x right here and take x squared and add 3x minus 28, if I were to divide this polynomial by x plus 7, what I should get out of it here is I will then end up with the other factor of x minus 4. Or vice versa, if I was to divide by x minus 4, I would get x plus 7. Now, I can quickly do this if I show the synthetic division. And if I put a negative 7 here, and then I have the 1, the 3, the negative 28. So I bring down the 1. Negative 7 times 1 is negative 7. This gives me negative 4. Here I get a positive 28. So I get a remainder of 0. And so you'll notice here that I have 1x minus 4. Doing the division allows us to break down the quadratic and get it down to another factor. And that's going to be our goal. So now we take a look at, well, here's a polynomial of a 3rd degree. So we would be having 3 solutions to this. Now the problem with this is that we can't factor this out. There are some factoring techniques that we can do with 4 terms. This particular problem right here is going to be real tough to do that with. So I want to show you how we can find our solutions a different way. And that is going to be by using what's called the rational zero theorem. What's happening here is as we start looking for rational numbers are any number. It's any number that can be written as a fraction. So 1/2 is a rational number. Well, so is 5, because 5 can be written as 5 over 1. So the rational zero theorem says that if a polynomial has integer coefficients, then any rational zero must be in the form of plus or minus p over q, where p is the factor of the constant term and q is the factor of the leading coefficient. So what we have to do here is we are trying to get ourselves to be able to determine what is possibly one of the solutions, all right? Because if we can find out one of our zeros, then what that can relate to is that can help us find a factor, and then we can do some division. So I'm taking a look at the same polynomial, and you'll notice here that the leading coefficient is 2, so that's going to be my q, and then the constant term is the 6, so that's our p. So we're going to be looking at the plus or minus p over q. So we're going to take the factors of 6. So factors of 6 are 1, they are 2, they are 3, and they are 6. Factors of 2 are nice because they are plus or minus 1 and plus or minus 2. All right, so now when I look at this, I have all these different possibilities. Now, if I were to list all of these out now, I have 1 over 1, so that gives us 1. And notice I've got the plus or minus because with the 6, I could do -1 times a -6 and get positive 6. I could do a positive 2 times a positive 3 or the -2. So we do have to consider all possibilities here. All right, so I have 1 over 1, I have 2 over 1, I have 3 over 1, and then I have 6 over 1. So I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. These right here are all possible solutions to our polynomial that we have. I also am going to have 1 over 2, 2 over 2, which is 1, 3 over 2, as well as 6 over 2, which is 3. So really I'm just adding on an additional 2 more here, adding on plus or minus 1/2, as well as plus or minus 3 over 2, so that's going to give us 3. All right, so now I'm taking a look at this and I'm saying these are all of my possible solutions to our polynomial. You'll notice here that we've got 1, 2, 3, 4, 5, 6. We've got 12 possibilities. However, since this is a third-degree polynomial, I only know that 3 of these answers are going to work. So this is going to be a little bit of guessing at this point. We are not using our graphing calculators at this point. Later on we will be, but since you don't have a graphing calculator for your test, we need to look at what are some other options. So what I'm going to do here is I'm going to go ahead and I'm just going to pick one of these. And I'm going to say, all right, let's go with +1. Let's see if we can go ahead and use that as one of my solutions. Now, if x were to equal -1, that means that a factor to go along with that would be x minus 1. Just like if I had x is equal to 2, the factor that's associated with that would be x minus 2. So what I'm going to do is I'm going to take my polynomial, I'm going to take f of x, and we are going to divide that by x minus 1. So I'm going to go ahead, I'm going to do my synthetic division. I'm going to put a +1 in the corner here. I have a 2, I have a -5, I have, I'll keep on this page, a -1, and then I have a +6. So I'm going to bring down the 2. That's a 2. 2 times 1, well, that gives me 2. -5 plus 2 gives me -3. -3 times 1 is -3. And then I'm going to go ahead and add that, and I get -4. -4 times 1 gives me -4, and here I get 2. Now, notice that my remainder is 2. What that means is my x equals 1 is not a solution. So positive 1 is not going to work. All right, so that's not a factor. So now I got to go back to the drawing board. So I'm just going to go ahead and erase this here. And let's just try positive 2. Okay. So I'm going to let x equal positive 2. So the factor that's associated with that is x minus 2. So now I'm going to take f of x, and I'm going to divide it by x minus 2. So I'm going to do synthetic division. You can do long division, but as you can see, synthetic division goes a lot quicker. So I'm going to have to put a positive 2 in that little box. And then I have the 2, the negative 5, the negative 1, and the 6. All right, so bring down the 2. 2 times 2 is 4. Add, and I get negative 1. Negative 1 times 2 is a negative 2. Add, I get negative 3. Negative 3 times 2 is a negative 6. And so, oh, look at that. We get a remainder of 0, which is awesome for us. So now, what has happened here is I have taken my third degree polynomial, I have divided it by x minus 2, and now I am coming up with a polynomial that is going to be a quadratic of 2x squared minus 1x minus 3. So I'm going to go back here in just a minute because I'm going to go back to this problem here. This is what we started out with. I took this polynomial here, I divided it by the factor of x minus 2, and now I got my polynomial here. Now when I came up with that answer, what is essentially happening here is after I divide this, f of x is now becoming x minus 2, that's what I divided it by, and then my answer that I came up with, which was 2x squared minus x minus 3. And so by doing the division, what that's doing is it's helping us factor out this third degree polynomial. I have been able to go from a third degree polynomial down to a second degree polynomial. In second degree polynomials, what we can do right now is we can usually factor those out. And this right here is a polynomial that we could go ahead and factor. 2x and x gives me 2x squared. Working with a negative 3x, and I have to keep in mind I need a negative 1 in the middle. So I'm going to go a negative 3 here and a positive 1. 2x times 1 is 2x. Negative 3 times x is negative 3x. That right there gives me negative 1x. So I have now completely factored this third degree polynomial by finding one of its rational zeros, which was positive 2. I was able to divide it by its factor and break it down to a second degree. So now that I'm trying to find my real zeros, trying to find all my x-intercepts, I can take each one of these factors and I can set it equal to 0. So x equals 2, which we knew that from the p's and q's. Here, add 3, divide by 2, so x is equal to 3/2, and then subtract 1, and x equals negative 1. So we'll notice that we have 3 solutions. Now, if I go back to the screenshot before here, notice that those are solutions that we came up with. The fact that we have the negative 3/2. Oops, did I? Oh, this is, sorry, I apologize. This is supposed to be a 3/2 there. Hopefully you caught that. But there's the positive 3/2 that I have. Positive 1 did not work, but negative 1 is going to work. And then we saw that the positive 2 was working for us. So all of those came up with from our P's and Q's. So what I would suggest for us to do is, actually that's the same one. Okay, so I'm going to go right here. Here's a new example, different problem. What I want you to try and do is I want you to try and pause the video, see what you can do on your own, and then start it back up and maybe kind of watch a little bit and then pause it again and try and Do as much of it as you can on your own. If you need to watch the whole thing through once, that's perfectly fine. But then what you can also do is go back and try and do it again. So I'm going to go ahead and explain the process, but you can go ahead and pause the video if you choose. All right, so I'm going to start with my possible solution. So my P's over my Q's. So I need to look at the two parts to this. We need to look at your constant term as well as your leading coefficient. And so your constant term right there of 50, those are your possible P's, and your Q's are the 2's. So I'm going to come up with all my different combinations. We're going to have a lot more in this one here. So I have plus or minus 1, I have plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 25, and plus or minus 50. With the other side, go ahead. All right, sorry I got interrupted, but we'll get back to it. So those are all my P's. Now I'm going to look at the Q's. Factors of 2 are plus or minus 1 and plus or minus 2. So we have a ton of different possibilities that are here with this function, okay? So I'm going to go ahead and I'm going to think about which one is going to work for me. So I'm going to save a little bit of time real quick, and I'm going to cheat on my endpoint. You just can't see what I'm doing yet. All right, so as I look at this, as I kind of look and I see, all right, what is going to be one of my solutions? And again, I'm going to take kind of a guess at this point. I'm going to take 5 over 1, okay? So I'm going to go ahead and say, okay, x is going to equal 5, which means the factor that we're working with is x minus 5. So we are going to divide our polynomial by the factor of x minus 5. So I'm going to put a 5 here. I have a 2, a negative 1, a negative 35, a negative 50. Bring down the 2. 2 times 5, so that gives us 10. This is negative 9, or sorry, positive 9. 9 times 5, so that's 45. This is going to give me a positive 10. This gives me a positive 50. And so the good news is here that I have a remainder. So now my polynomial has been brought down. So since I've divided here, now f of x has now become the factors of x minus 5 times 2x squared plus 9x plus 10. Okay. So now if I wanted to, I could go ahead and try and factor this out. X minus 5. Let's see, 2x squared, so that's 2x and an x. And I need to get a 9x in the middle, and I have a 10 to work with. So my options here would be 2 and 5. So let's see, that would put, if I put a 5 here and a 2 here, will that give me what I want? Actually, I think I've got to flip those around, sorry. That's the beauty of factoring sometimes. So I actually want to put the 2 here and the 5 here. So 2x times 2 is 4x, 5 times x is 5x. That right there gives me my 9x. So now I'm able to factor this out, and I'm going to now set it equal to 0. So each factor is going to equal 0. X minus 5 equals 0, 2x plus 5 equals 0, and x plus 2 is equal to 0. This tells me that x is going to equal positive 5. Here x subtract a 5, divide by 2, so negative 5 halves, and x equals negative 2. So I have my 3 solutions. They're all real solutions as well. All right, so I'm just going to kind of do a full screen here. Not that, sorry. On full screen. Entire page, that's what I want to look at. So again, going from a third degree polynomial, I'm going to be using one of my zeros and trying to figure out which one of those rational zeros would work. Again, this one I cheated and I looked at something to help me figure out what it was going to be, just for time restrictions on this. All right, so now what do we do when you get a situation where, you know, like that just popped up there, and sitting there and working with all these P's and Q's and doing all of that? That is not always going to be in the best of our options, because there's other things that we can do as well. And graphing and helping us do that is going to be the best way to do this. Now, I'll show you how I cheated on this last problem. This polynomial is the exact same one I just did. Now, in order to look at this, and rather than go through all of those different options that we have, what I did was I cheated. I actually graphed it out onto my graphing calculator, and I am trying to look for what I call are some obvious zeros. So when I look at this graph right here, I can see that my graph is going through the point here at x is equal to 5. And so if it goes through at x equals 5, that means that that is one of my solutions. And so I'm going to go ahead and divide our polynomial here by x minus 5. And that's what I did. And so then once I divided my polynomial, and we ended up with, sorry, I got to go back here, 2, 9, 10. So then we had our 2x squared plus 9x plus 10, okay? Then I was able to factor it once again. And if I were to take a look at the different solutions that we have, and this was x, I can't remember which ones I did, plus 2, and this is x plus 5. Once we solved this and we got that x is equal to 5, we have x is equal to negative 5 halves, and x is equal to negative 2. Those are the other solutions that are popping up here. So we've got negative 3.5, or negative 2.5, sorry, negative 2.5, as well as negative 2 for our solutions. So graphing it out is going to be super helpful. For example, now we look at a fourth degree polynomial. All right, so finding your P's and Q's is just not going to be the most fun to do, and also it's a little time consuming. So I want to show you how you can shorten this up a little bit, and how we can look at the graph of this polynomial to help us figure out exactly what your solutions can be and how you can go about this. All right, so I have to go back and do a few things here. First of all, I'm going to clear out my equations, do that, and then I'm going to do the standard window. So zoom 6, that gets me into my window. So now if I was to go ahead and plot this out, so 3x to the 4th minus an 8x to the 3rd minus 33x squared plus 62x plus 24, and I graph it out, I end up with, and I'm going to go to my next slide right here, I get this graph. Okay, so there's my graph. Now if I look at this function right here, I should be able to find some real zeros and some obvious zeros. Notice I see one right here, and that looks like 1, 2, 3, 4. Notice it looks like there's one right here, and that's at positive 2. So to help me break this down, what I'm going to do is I'm going to take my polynomial and I'm going to divide it by one of those factors. If x is going to equal 4, then that means that I could divide it by the factor of x minus 4. So I'm going to use synthetic division. I'm going to take the 4, put it in the box here. I've got the 3, the negative 8, the negative 33, the 62, the 24. Okay, I'm going to drop down the 3. 3 times 4, so that's 24, or sorry, 12. Negative 8 times 12, so that's